Ever look around and just marvel at the sheer variety of stuff that
Oh,
exists? A
absolutely.
wispy cloud, a solid steel beam, the water in your glass. I mean, they're all fundamentally different.
Totally different properties.
But has you stopped to think about what makes them that way? What's the secret sauce at the tiniest level?
Yeah, what dictates whether something is hard or soft, conducts electricity or, doesn't?
Exactly. That's what we're diving into today. Chemical bonding.
Yeah.
Sort of the invisible forces holding everything together.
Precisely. Think of it as unlocking one of nature's most elegant secrets. How these seemingly independent atoms link up.
To make everything we see and touch.
Right, to create the entire material world. And at its core, the idea is actually quite, well, intuitive.
Okay.
Imagine atoms as individual Lego bricks. Chemical bonds are just the ways these bricks snap together.
Ah, the little connectors.
Exactly. To form more complex structures, molecules, larger networks, you name it. And the key players in this whole atomic construction game.
Let me guess. Electrons.
You got it. Specifically, the outermost electrons. We call them valence electrons. They're the ones doing the connecting.
Okay, so these valence electrons are the crucial bits. Why is understanding this connection so, well, fundamental?
It's absolutely foundational. I mean, without these chemical bonds, atoms would just be floating around alone.
Isolated particles?
Right. The incredible diversity of substances we see every day, it just wouldn't exist. Take water, for instance. H2O. It's the specific way hydrogen and oxygen atoms bond that gives water its amazing life-sustaining properties.
Like dissolving things.
Like its ability to dissolve so many other substances, exactly. Or think about a diamond. Its extreme hardness isn't some kind of magic.
It's the bonds.
It's the network of incredibly strong bonds between its carbon atoms. And conversely, the way electrons are shared in metals allows, the device you might be listening on right now,
Fun, yeah.
to conduct electricity. The type and strength of these bonds, they basically dictate everything.
Wow. It's kind of mind-blowing that something as basic as how atoms link up explains, well, everything from water to iPhones.
It really is.
So how do these links actually form? What are the main ways atoms get together?
Okay, so there are three main types of chemical bonds we should probably focus on. The first one is the ionic bond.
Ion. Okay.
This kind of bond typically happens when a metal atom interacts with a non-metal atom. And the crucial thing here is the transfer of electrons.
A transfer. Like one atom just gives an electron away to another one.
Precisely. The metal atom, it tends to lose one or more of its valence electrons.
Okay.
And when it loses those negative electrons, it becomes a positively charged ion. We call it a cation.
Cation. Got it.
The non-metal atom, on the other hand, is happy to accept those electrons. It becomes negatively charged an anion.
Anion, negative.
Yeah.
Cation, positive.
You got it. Now, remember that basic physics rule? Opposites attract.
Right.
So these new ions with their opposite charges are really strongly drawn to each other. That attraction is the ionic bond.
Ugh, like magnets snapping together. Positive pole, negative pole.
That's a great analogy. The positive and negative charges are the attractive forces. And, beyond just holding salt together, these strong forces in ionic compounds often mean they have high melting points.
Right.
And they tend to be brittle. Think how easily salt crystals shatter compared to, say, bending a piece of metal.
That makes a lot of sense.
Yeah.
So can you give us a really concrete example, something common?
Oh, the classic one is sodium chloride, just plain old table salt.
NaCl.
Exactly.
Yeah.
Sodium Na is a metal. It has one valence electron. It's pretty eager to get rid of. Chlorine, Cl, is a nonmetal, and it really wants one more electron to get stable.
Perfect match.
Kind of. So sodium transfers its electron over to chlorine. Sodium becomes a positive sodium ion, Na+. Chlorine becomes a negative chloride ion, Cl-, the anion.
Right.
And then these oppositely charged ions arrange themselves in this repeating 3D crystal lattice structure because of that strong pull, the ionic bond.
Okay, ionic bonding, give and take electrons, get charged particles, they stick together. Got it. What's the next big way atoms bond?
So the second major type is the covalent bond, and this is quite different because instead of a full transfer,
No giving away.
no, here we see a sharing of valence electrons, usually between two or more non-metal atoms.
Sharing is caring, even for atoms. How does sharing actually create a bond?
Well, by sharing electrons, each atom involved can kind of count those shared electrons towards filling up its own outer shell.
Ah, so they both benefit.
Exactly. They both reach more stable configuration that way. Think of it like Two people holding hands.
Okay.
They're both contributing to the connection, and holding hands keeps them together. And importantly, covalent bonds aren't just one type of sharing. They can be single.
One pair of electrons.
One pair shared, yes.
Yeah.
Or double sharing 2 pairs, or even triple sharing 3 pairs.
Wow.
And this ability to share multiple pairs, especially by atoms like carbon, is really the foundation for the incredible complexity of organic molecules. You know, the stuff life is made of.
Right. Different sharing patterns must lead to different shapes and properties.
Vastly different properties, even with the same atoms involved sometimes.
So what's a common substance held together by these covalent hand-holding bonds?
Water is the perfect example, H2O again.
Right.
One oxygen atom bonded to 2 hydrogen atoms. Oxygen needs 2 more electrons for a full outer shell. Each hydrogen needs 1 more.
So they share.
They share. The oxygen shares 1 electron with each hydrogen, forming 2 single covalent bonds. Everyone's happy.
Nice. Any other common ones?
Methane, CH4, main part of natural gas.
Okay.
Carbon needs 4 more electrons. Each hydrogen needs 1. So carbon shares 1 electron with each of the 4 hydrogens. 4 single covalent bonds.
Right. So ionic is transfer and attraction. Covalent is cooperative sharing. What about the third type? Metallic bonds. Sounds like it's just for metals.
You're spot on. Metallic bonding is pretty unique, and it explains why metals behave the way they do.
Oh.
In a chunk of metal, the valence electrons aren't really stuck to any single atom. Instead, they become delocalized.
Delocalized, meaning?
Meaning they're free to move around. They form what's often described as a sea of mobile electrons that flows throughout the entire metal structure.
A sea of electrons. That's a cool image. How does this electron sea hold the metal atoms together?
Well, imagine the metal atoms themselves as positively charged ions, arranged in a kind of grid, a lattice.
Okay, positive ions sitting there.
Right. And these positive ions are basically swimming, immersed in this sea of negatively charged electrons. The attraction between those positive metal ions and the negative electron sea is the metallic bond. It's a collective sharing, really, across all the atoms.
It's not just between 2 atoms, but the whole group.
Exactly. And that sea of electrons isn't just glue, it does other things too. It acts like a sort of cushion.
A cushion.
Yeah, letting the metal atoms slide past each other without breaking the whole structure apart. That's why you can bend a paperclip, you know, but a salt crystal just shatters.
Right. And the sea must be why metals have their typical properties.
Absolutely. That mobility, the freedom of those electrons, is key. It's why metals conduct electricity so well, the electrons can easily carry charge through the material.
Makes sense.
Same for heat. They transfer thermal energy efficiently, making metals good heat conductors. And that malleability you mentioned, being hammered into sheets, and ductility being drawn into wires.
Like copper wires.
Exactly, like copper wires or iron nails or gold jewelry. That all comes from this delocalized bonding. The atoms can rearrange because the sea holds it all together flexibly.
This is really fascinating. So these 3 fundamental types, ionic, covalent, metallic, they're like the primary rules for how matter puts itself together.
Pretty much, yeah. At the most basic level.
It's incredible to think how these tiny interactions have such massive effects on the world we actually see and interact with.
Oh, the impact is everywhere. I mean, think about buildings, the structural integrity.
Steel beams.
Steel beams held together by strong metallic bonds, or the clothes we wear, often made of polymers.
Plastics and fabrics.
Right, long chains of molecules linked by covalent bonds, giving them flexibility and strength. And, like we touched on, our own bodies rely completely on chemical bonds. DNA, yeah, the blueprint of life. Held together by specific covalent bonds, and also weaker hydrogen bonds, which are crucial. Or think about how oxygen gets carried in our blood.
Hemoglobin.
Right, bound to iron atoms through a mix of interactions involving ionic and covalent character. It's almost hard to believe these 3 basic atomic rules govern the whole material world.
It really is almost mind-boggling when you connect the dots like that.
Yeah.
Even things we take for granted. Food, medicine.
Totally. Food we eat, medicines we take, it's all about specific atoms bonded together in very precise ways to make molecules with unique effects and properties. And understanding bonding isn't just about explaining what's already here, it's vital for innovation.
How so?
Well, scientists and engineers can design and create totally new materials with specific, tailored properties because they understand these bonds.
Like making something super strong but lightweight.
Exactly. Lightweight alloys for planes or spacecraft, advanced polymers for medical implants. It all comes down to understanding and controlling how atoms connect.
So, okay, let's try to bring it all together. We've really dug into what holds matter together. What are the absolute key takeaways for listeners?
I'd say the most important thing is that chemical bonding is the fundamental force driving how matter assembles and behaves. Full stop.
The why behind structure.
Right. And atoms do this. They bond to get more stable, usually by filling up their outer electron shells, lower energy state.
Okay.
And this happens in three main ways. Ionic bonds through electron transfer,
Give it take.
covalent bonds through electron sharing,
Holding hand,
and metallic bonds through that delocalized sea of shared electrons.
the electron soup.
Yeah, the electron soup. And crucially, the type of bond dictates the properties of the substance. Hardness, conductivity, melting point, it all flows from the bonding.
Leading to the incredible diversity of materials and all their uses.
Precisely.
Okay, so we started by wondering how the world gets its structure, why things are so different. And the answer really seems to be these different types of chemical bonds, the essential atomic glue.
That's a great way to put it, the atomic glue. These seemingly simple interactions at the micro level create all the complexity we see at the macro level.
This has been incredibly illuminating, really, thinking about how these fundamental forces shape literally everything. It really sparks a sense of wonder.
It does, doesn't it?
It makes you think, what other simple-seeming interactions might hold these huge, complex secrets about reality? Like, I don't know, gravity at the quantum scale, or the forces inside an atom's nucleus.
So that's a fantastic point.
Yeah.
Where else are these fundamental roles playing out in ways we haven't fully grasped?
This deep dive into bonds feels like just scratching the surface of this huge interconnected picture.
Absolutely. And hopefully, now that folks have a glimpse into how atoms connect, maybe some new questions pop up.
Like what?
Well, maybe you look at a piece of metal differently now, thinking about those free electrons, or appreciate the balance of sharing in just a drop of water.
Yeah, seeing the unseen connections.
Exactly. The journey of understanding often starts with these building blocks, and there's always, always more to explore.
Absolutely. It definitely leaves you with a profound sense of awe for these invisible forces shaping our reality. Thanks so much for taking this deep dive with us.
My pleasure. It was fun.
Until our next exploration, everyone, keep that curiosity burning.